The views and opinions expressed in the following program are those of the participants and do not necessarily reflect those of KSMQ Public Service Media Incorporated or its assigns.
Welcome to the 10th Regional Town Hall as part of KSMQ's Cities on the Move series. Tonight we're looking at the weather. Weather is fascinating. It affects our daily life. It's exciting and it's always changing. I'm your host, Stephanie Passingham. Stay tuned for an informative and engaging discussion coming up on Cities on the Move. Tonight we'll be exploring the hot, cold, wet, dry, windy influence that weather has on our region. We'll look at long-term trends that lead to climate change discussions. We'll explore some of the new technology that makes weather easier to predict and easier to understand. And to wrap it up, our guests will share some stories about interesting weather events. Please welcome our guests now. We have Minnesota State University Mankato Department of Geography Chair, Dr. Don Friend. Service Coordination Hydrologist for the National Weather Service, Steve Buin. Minnesota Assistant State Climatologist, Peter Boulay. Executive Director of the Iowa Academy of Science, Craig Johnson. Iowa State University Extension Climatologist, Alwyn Taylor. University of Minnesota Professor, Dr. Kathy Klink. Well, thank you, all of you, for being here, and we'd also like to welcome the members of our at-home audience, and we'd like to invite them to join us anytime by making a comment or asking a question, either by phone or email. The phone number is 1-877-4MY-KSMQ. That's 1-877-469-5767, or email us at ask@ksmq.org. We're going to open our discussion this evening by talking about one of the most controversial topics in weather, climate change. Let's start right here.
Weather. It's something we all talk about. Weather is a common experience that draws people together. Millions of conversations are started with a simple comment about what's happening outside. Weather has an enormous impact on our personal and professional lives. Rain brings nourishment of crops and spoils picnics. Warm, sunny days are perfect for bike riding, but drive up energy consumption. There's always something to say about the weather. Scientists who have been studying the weather are pointing to some changes in our climate. The working group of the Intergovernmental Panel on Climate Change reports that surface temperatures have risen 0.74 degrees Celsius in the last 100 years. That doesn't sound like much, but what does it really mean? Climate change, global warming, global water crisis, whatever you call it, it is one of the most discussed and debated weather topics.
Well, this conversation clearly gets a lot of play in the media and in conversations among all sorts of folks. And I ran across an old article that said another ice age. So my question is, Kathy, they talk about such a small degree of change, and this is hard to predict, I'm assuming. Tell us a little bit about prediction of these long-term trends and what such a small degree of change means.
The prediction of long-term trends within climatology, the things that, say, the IPCC, the Intergovernmental Panel on Climate Change, is using, those are all of the projections are based on climate models. And climate models are essentially built from weather prediction models, which we've been using for 40 years and keep getting better and better. And so do the climate models. And so that's why every so often, every 7 to 8 years or so, the IPCC will come out with a new report, because it's sort of updating us on what we know about the prediction of climate change. The small changes that that documents like the IPCC will talk about, 0.74 degrees Celsius, which is just a little over 1 degree Fahrenheit as a global average, doesn't sound like a whole lot, but to kind of think about back in the Little Ice Age, about 1650 to 1750, when it was at its coldest, it was about a half a degree Celsius cooler than our temperatures right now. So just to go on an average, a half a degree Celsius, which is a little under 1 degree Fahrenheit cooler than we are now, put us in something like the Little Ice Age, where we had crop failures and all kinds of things going on. So relatively speaking, from a climate change point of view, that's a fairly substantial temperature change.
All right. And when we were in the 70s and we were talking about possible ice age, how far out? Give us a sense of, you guys are all in the business of predicting or have some experience predicting. How difficult is that?
Well, one thing that's kind of interesting in our office, we have an old book that was published in the 1980s. It's called Climate Change to the Year 2000. Okay? So we have a lot of fun going through this book and saying, well, were they right or not? And in this book, there's a plot. And there's graphs showing temperature using different models going up on the extreme end and on the real low end, and right in the middle was about the same change we saw to the year 2000. So back then in the 80s, the middle range of the models got it right. So that's one way, at least you can see how their previous success, and maybe it'll give us some idea of the future.
It's also kind of interesting, in the 70s, when there was interest in global cooling, or there was some talk about global cooling, the temperature records were actually not cooling that much except in the northern hemisphere land areas. If you looked at the southern hemisphere, there was research going on at the time that actually showed the southern hemisphere was not cooling. And so to some degree, some of the things that we hear about are part of our own bias of, we live in the northern hemisphere, most of us scientists and most of the people who are in the world live in the northern hemisphere, so we have that kind of sort of conception of of what's going on in the world. And it's neither good nor bad, it's just kind of the way it is. And so I think there certainly were people who were interested in global cooling, but at the same time, during that time, there were also people, probably an equal number of people, who were worried or interested in things related to warming on the other end.
I think we also have to consider, in doing climate prediction, the scale of the amount of time that we're considering. And so for the past few minutes, we've been chatting, the last few hundred years, since the 1980s. When we start thinking paleoclimate change, we have to look to the fossil record. How long does it take glaciers to melt? On the order of thousands of years. On the order of hundreds of thousands of years, we've had ice ages come and go. And so to the public, this is confusing. Well, we used to have ice ages. The planet's been warmer in the past than it is now. Why is this global climate change when it's been warm? Are we going to have glaciers running over Iowa when we had an Iowan glacial state? So these are, when I teach this in a class, it takes a whole semester to explain all these things. And so we always have to consider the scale at which we're looking. Are we talking the last 20 years? Are we talking since the little ice age 300 years ago? Or are we going back 300,000 years? And on what kind of scale? On a human time scale, this always matters. What's going to happen in my lifetime? What's going to happen in my grandchildren's lifetime? And this decadal kind of change, this is what we have to try and predict now. How do we react to it with our economy, industry, infrastructure, based on all different scales of background? How do we do this?
That's a good question. We have this information that says that temperatures may be warming a little bit. So if it's not going to happen for thousands of years, so what? What kind of action is necessary at this point? Why do you think that's a...
And one of the issues with this is just how accurate are the climate models when it really gets right down to it. Because in the 70s, the models were actually, some scientists predicting like a coming ice age. Those were the headlines. If you look at how the models were running back in the 80s and 90s, they did over-forecast the warming of the last century. And when you look at, they were essentially retuned, and tuning is changing some parameters in there to make them match the past. And they have predicted continued warming through this next century. And in fact, we're not 10 years yet, but we're getting close. The planet has actually cooled. So the trend in the model forecast since 2000 has been for a rise. In actuality, the temperature has been cooling. So there's something missing in those models because it's not catching this, at least so far.
So let's talk about a little bit what might be causing this and why we might want to make some changes, regardless of what might happen thousands of years from now.
When you think on this decadal change and the masses of humanity, more than half the populace of the globe lives on the coasts. And for ice to melt and sea level to rise an inch or two, this doesn't affect trade or infrastructure particularly, but if sea level rises 6 inches, which it's actually starting to happen a few inches in a few places, well, whenever you get a big storm, it's wiping out people who live on shallow islands. Now imagine the country of Bangladesh, none of which is above, about 10 feet above sea level, and 300 million people live there. Where are they all going to go? The state of Florida. Everybody, the highest point in the state of Florida is a garbage heap. It's a landfill. And if sea level rises a few feet, where are all these Floridians going to go? This, for me, this is a very big issue.
Interesting.
Yeah.
And to bring it home to the region, what would the impact be on our region if warming continued and sea levels rose? And what are people going to experience right here at home?
Well, I think here in the Midwest, we're the agricultural production capital of the world practically, and if it changes what kind of crops can grow here, or just what land is if too much water, not enough water, it could significantly change the economy. And I don't know that we necessarily have the capacity to adjust to that, because we're in a kind of a just-in-time world now, and we don't have. I don't know that we necessarily have seasons to adjust. We may have. I don't know that. Dr. Ellen Taylor could probably answer a little bit more. How much reserves do we have to make adjustments in agricultural production?
Agricultural production is a big question, because people say, well, if the climate changes and Texas's climate ends up in Iowa and southern Minnesota, where will the corn production be? I have to remind people, corn grows in Texas. So agriculture can adapt to these things really quite well. The agriculturists are very resourceful and clever about it, but don't think that it wouldn't be without expense and frustration.
Mm-hmm. Elwin, do you think that's maybe overly simplified, because we need the soils? We need the right kinds of soils that are provided by the climate. So Texas, the heat is there certainly, but we need the water, and where are you going to get all the water? In an arid climate, semi-arid climate, and also the appropriate soil type to grow the volumes of grain there that we grow here in this region.
The thing to remember is our soils are a product of the climate.
That's right.
The climate of the plains generated the soils, if you will, caused that soil genesis in this area for the finest soils for growing things on the earth. Yeah. If the climate changes, then we don't have the climate support of the soil type, and it begins to change over the years. In other words, it becomes a greater task to keep the rich, productive soils.
Yeah. All right.
So if we think maybe there's some question of the modeling and we're not really sure there is long-term global climate change, let's presume there is. What kind of advice do you have for everyday viewers about what they should do at this point in their lives to address this, whether it's adapting themselves, changing behaviors? Are you even recommending change of behaviors at all? What's your advice?
Well, what I always tell people that ask me that question is don't even think about climate change per se. Think of the natural variability of climate itself. We will have another drought. We will have another flood. That's just part of Minnesota's climate. Yes, climate change will definitely be part of that, but also don't forget that the natural variation of climate will still be there. We haven't seen everything in Mother Nature's bag of tricks yet, so there will probably be something out there that'll exceed what we've already seen in recorded history. So, don't lose sight of just the normal variation too. That's what.
I think we have to be careful about assuming we can affect climate change ourselves as human beings. I think that's a stretch. When you actually look at the computer models, the forcing in those models doesn't come from carbon dioxide. Carbon dioxide does start the warming, but it's how the model handles water vapor is what allows the temperature to take off. And there's a lot of disagreement about whether water vapor is a net warming or cooling. In fact, there's a lot of studies right now talking about the fact that water vapor actually is a net cooler because of the cloud cover, the changes in cloud cover, which can reflect more heat back to space. So, there are a lot of issues that need to be looked at when need to be considered when you look at this. And the evidence doesn't support that carbon dioxide actually drives the climate. There are other factors that get involved here, and some are external, like the sun.
Actually, I would take a little bit of issue to that, if I might. I think that water vapor is by far it's the most important greenhouse gas. There's no doubt about it. Just because there's so much more of it in the atmosphere than CO2, carbon dioxide, or methane, or all these other things. the models certainly do have issues with water vapor. And one of the things with water vapor is, depending on cloud cover, if you have low clouds, then the water vapor in the cloud cover acts as cooling. But if you get high clouds, then the water vapor acts as a net warming effect. So there is certainly a lot of uncertainty in the climate models about what's going to happen with cloud cover. That's not the part I'm going to argue a little bit here. But I think that the role of greenhouse gases such as carbon dioxide, which we know has been increasing in the atmosphere, there's absolutely no doubt about that. No one's going to argue that there's not an increase of CO2 in the atmosphere. And we know that CO2 is a greenhouse gas, and so there is a direct effect of CO2 by having it absorb the radiation that helps lead to warming. But there are also all of these secondary effects, the effects of warming on the hydrologic cycle, so exactly what you're talking about with the changes in cloud cover. We could have changes in just the general humidity of the atmosphere. And so there is some evidence that the water vapor content of the atmosphere itself, regardless of clouds, has been changing. And the other thing with the models, given all of their uncertainties, which I'm well aware of, I actually teach a class in climate modeling, and I try not to make everyone feel like, well, climate models are just totally out to lunch, because they're not totally out to lunch. Remember, they're coming from weather prediction models, and we know that weather prediction models, they're not perfect either, but we still rely on them, right? The climate models, if they do not include the anthropogenic signal of CO2 in them, if you run the climate models without the CO2 forcing, they cannot replicate the observed mean temperature change of the globe. If you put CO2 in, then they can. That was one of the big things that came out of the IPCC document. That I think it's been in the last few, but in this last one, certainly, there's a lot of comparison of if we run the models without CO2 and if we run the models with CO2. And if you run the models without CO2, you cannot replicate the observed pattern of temperature change.
But that assumes that CO2 is the only other factor that could cause that warming. And there are other external...
Not necessarily, but yeah.
There are other external factors like the sun. I mean, there are scientists studying the sun showing that increased and decreased solar activity corresponds very well with the rises and falls in Earth's temperature.
Oh, yeah, for sure.
And over the last century, the sun... the sun was more active, and right now we're in a period where we're not getting the sunspots back when we normally should. So there's some conjecture, at least, about is the cooling we're experiencing right now related more to the sun than anything else?
And that's certainly true. You're right about that.
And if we go back and look at the Vostok ice cores, that actually shows temperatures, carbon dioxide rising after temperatures rise. So that suggests that temperature is preceding the carbon dioxide rise under those conditions. The last century, we all agree we had a consistent CO2 rise in temperature, but from like 1912 to 1942, temperatures went up. From 1942 to 75, they went down. From 75 to 98, they went up, and then after 98, they started coming down again. So, and CO2 is increasing that whole time. So, clearly there's something else going on in here, and at least in this century, models are not picking up this cooling. There's something else happening. So
that I'm not going to argue with.
Steve, let me jump in for a second. National Weather Service does a lot of tracking of kind of collecting data, and the same thing with the State Climatology Office. Guys, talk a little bit about whether the collection of data has fostered some of this debate that occurs. We just know more, but maybe we haven't stitched it all together. Talk about how kind of data collection and prediction has changed, and there's just more information out there.
Yeah. Well, there may or may not be more information out there. It's getting hard to recruit people to actually observe the conditions. But yes, the techniques and things have changed over time. With some of the older viewers will remember liquid and glass thermometers. If you asked a viewer under 20 what a liquid and glass thermometer is, they probably couldn't tell you. And so we've gone to electronic observing, which through our scientific study is found to be more accurate, more precise, can respond quicker, so we can observe more rapid changes in things like temperature. So you get some of that debate in there too. So there's a lot of things to debate, much like we've seen here at the table already tonight, is that the changes in observing systems, some people will debate that, the urbanization of a lot of parts of the globe, changing the landscape, and maybe that's causing temperature. Well, if that's true, then that's what is actually happening. It's not regardless, the urbanization is, we've changed the landscape. We're measuring the temperature over the landscape that exists at that location. So I throw that argument out, is that people talking about, well, you're measuring an urban area. Well, of course we're measuring an urban area. That's what it is. We can't just measure the Earth's temperature over a pristine natural prairie forever, because there's very little of that left. So I'd argue that the measuring is being done appropriately all across the world, because the world's changing.
I'd like to add something there. The advent of satellites in space and some of the observations they have done about the gases and the changes in the nature of our atmosphere, this is huge. We would not have understood anything about ozone depletion over the poles without satellites. We wouldn't have gotten it at all. And so the fact that we have some of these new tools, this is helping us to do a better job. And yes, we're having fewer and fewer weather observers to get out there in their backyards. What's going on?
Absolutely.
That's tough. But by the same token, we are now trying to set up networks across the globe, gridded networks, and we know exactly where we do and we don't have data.
Well, and perhaps this is a beautiful segue into our next segment of the program, where we talk about technology. Technology has changed our lives in so many ways, and new tools are at the ready for weather prediction and interpretation. So let's take a look at a quick tape.
With the advent of the internet and sites such as weather.com, many people are taking a more active role in exploring the weather that surrounds them. We are becoming experts at predicting the weather, or at least we think we are. Where does that leave the local weather meteorologist? New technology is developing more creative ways of describing and predicting what is coming our way. What are the limits, and what can we still learn about the weather through projects such as Vortex 2?
Well, weather.com is one of my favorite sites. I check it in the morning, and what's my day going to be like? And sometimes it's accurate, and sometimes it's not. Now, you have many years of history as a weatherman. I'm going to start with you, Craig, and tell us a little bit about what you think of sites like weather.com, or resources that individuals turn to instead of perhaps flipping on the TV.
I think they're great. I mean, I think people have to realize, what their limitations are. And and of course, weather.com. There's also weather.gov, which is National Weather Service. I really like that one. So, but they're both fine. The data or the forecasts, for the most part, originate with the National Weather Service. And so any of those sites provide a wealth of information. I mean, it used to be you had to watch TV to maybe see a radar image or something like that. To me, it's just fantastic that we can sit down at a computer at our home and we can look at satellite imagery and radar and current weather forecasts, and all those tools are on there. Mm-hmm. Now, you got to be careful. You don't want to be the person saying, okay, I can predict a tornado or something because I can see a radar on the screen. You have to understand it. So the other side of this is that people need to understand what they're looking at. And so the plus is it's there. The minus is, how do I use that?
Mm-hmm. You were mentioning, Steve, too, about on-the-ground personnel. Are they still necessary? And it sounds like maybe there's a shortage of some of those folks.
Yes, on-the-ground people are very important. Don mentioned we are deploying some electronic networks out there, but we still rely on, for instance, we use the radar. We see people might see it as saying, oh, it's just raining there, or that's where they're saying there's a tornado or a hail or something. But as a hydrologist, we use the radar to quantify how much precipitation fell. And it's those ground observers that are out there that tell us, okay, in the last 24 hours we had 3 inches of rain. What does the radar say there? And the radar, may plus or minus a little bit. Well, then we can have confidence to translate that the radar's quantifying it accurately where we don't get a ground report. And that's invaluable in hydrology, to be able to have confidence of how much water fell on the landscape. So we rely on the ground reporters there, and also in severe weather. There's severe weather spotters. Very essential to go out and actually look for actual verification that a funnel cloud is forming. The radar can throw you off. Even the professional trained meteorologist can be thrown off on a tornado signature for some other reason, and so it's important to have someone out there spotting.
I agree. There's always going to be a role for eyes on the ground with spotting for tornadoes, and when you mentioned, Steve, verification of radar, Minnesota's blessed with having 1,500 volunteer rain gauge readers out there in the state. So in some counties we have so many gauges we wonder if the rain actually reaches the ground sometimes. But those gauges are really handy for verification, especially when flash floods can be very localized. There's a big difference between getting almost 7 inches of rain and 4 inches of rain in a model. So if we can relay that information to the Weather Service, that definitely helps them out.
And that's a good point, is that you need this verification on the ground, because all those tools have their strengths. Radar sees certain things, there's things it doesn't see. Same with satellite imagery. All the remote sensing, there's things they see and things they don't see. So you still need the eyes and ears and the people to measure things on the ground.
That's a great point. This morning was a perfect example. I checked my weather. We had an on-location shoot outside. I looked, there was no green on the map anywhere. I got to the gas station, was filling my car, and it's a heavy drizzle. Why is it? Let's talk about the limitations of why can't you, whatever satellite, or why can't they see that rain?
Well, radar, the smaller the drop side, the harder, because it's a certain wavelength of radiation that's going out and it's being reflected off of something out there, and it's the weather radar is actually tuned to spot a certain size of hydrometeor, and so when it gets so small, it just does not get enough energy back, and so it's the energy back that is actually what you see depicted on the television when you see the different colors in that. That's actually a reflection. It's a quantification of how much energy came back, and so the more energy come back, the larger drop it hit.
Okay.
So heavy drizzle, it's not going to see that.
And a radar beam doesn't hug the ground.
Yeah.
Right.
I mean, the farther you are away from the radar, the higher up the beam is.
Yeah.
So it's seeing things progressively higher and higher. So that's the other side of it too.
Interesting. Weather prediction is a challenge, and I know often folks sit in their armchairs and say, "Oh, I could have done a better job than that." Talk about what tool you would love to have in your toolbox that you don't currently have, and what would it tell you about the weather that's important to the work that you do?
I want the Star Trek, like they had in one of the movies, the climate or weather amelioration system. Get rid of this.
There you go. One thing I remember in going through college was I wish there was a more denser upper air network, because your computer models are all, no matter how fast you get, no matter how much whiz-bang computer technology you get, they're all going to be limited by the data you put in there. And if you only have 2 upper air balloon launches per state, that's the best you're going to get in the upper level. Now there's other tools out there, I'm a little removed from it, but I remember on the wish list, if you could wish anything in the sky, it would be more upper air observations, maybe more frequently. I know sometimes, Steve, they do launch a special one if there's severe weather.
Yeah, severe weather, they'll launch an extra one, but that's a very, very labor-intensive thing to monitor the kind of the lower part of the atmosphere. Satellites do good; they see the top of the atmosphere, but most of the action is in the lowest half of the atmosphere, which really, I don't mean physical half, I mean half of the mass, and that's up I think about 20,000 feet or something is the first half. And so we need to monitor that with balloons that carry an instrument up that measures the humidity and the temperature, and then to calculate the wind speed by tracking it. And it's a fairly expensive proposition, on the order of about $100 per launch. So.
So when you see these sweeps of this low fronts coming through or this high pressures coming through, and here you watch those predictions on whether it's your local news channel or weather.com, how do you guys make those predictions?
Well, if you're watching television, almost all of those are straight out of a computer model. And so the person on the air would be picking which one to use. And so that would show you how a computer was forecasting storms to move. Now, the Weather Service might change their forecast and maybe not follow a model exactly. And talk about that.
The biggest change would be in the first 24 hours. is you're actually tracking the physical weather, like timing a front coming down from the Dakotas, or like an Alberta clipper in the winter. The experience tells you whether the computer models can accurately depict that or not. And so that first 24 hours, maybe 2 days, you're tuning it a little more based on experience. You get out past that 3 to 5 to 7 days, a lot of that very computer driven. But in relaying a lot of information to the public, Elwyn is one of the greatest resources being an extension climatologist, he contacts probably personally the most people in any given state. You know,
He does.
and that's what really gets, that's the education aspect. That's that outreach education that's so important, is that we're at the Weather Service and we're in Chanhassen, Minnesota, and our ability to directly impact people, you know, face to face is very limited. But we rely on Elwyn and Mark Seeley here in Minnesota to really take it to the people. And maybe Elwyn could talk about that, about how that works, of bringing it out to the people.
This whole discussion is so delightful to me. I spent my first 3 years working with weather with the upper atmosphere, right, where you would like to have more information. I spent my next 6 years with the National Weather Service. And the thing I learned in the National Weather Service was not to trust the models. I used to give papers in Washington with Dr. Klein sitting there, the fellow in charge of the model. And I remember in the time I talked about, we have a Moss forecast to cover up the total failure of the numerical models. And everyone gasped, except Dr. Klein, who was responsible for it. Well, we have these things developing, but still, in the morning, I would sit down and I'd look at the weather map of what had happened. And I would take my blank piece of paper that showed a map of the area I was interested in, and I'd draw for 12 hours, I'd draw one for 24 hours, I'd draw one for 36 hours, and then I would look at the model. And when they disagreed with my piece of paper, I looked for where I'd made my mistake. And I'd usually find it. And sometimes I wouldn't. And when I couldn't find what I'd done wrong and why the model disagreed, I went with me. I made it for a full year without a wrong forecast. We try to teach that to our students. But we have to remember, weather is not a totally random thing. It's physics. It's physics of the atmosphere, and it obeys the laws of physics. And so this is the important thing for us to remember, that we are going with an absolute science, even though we do not have absolute forecasts. We have a lot of approximations that go in them. We were talking a few minutes ago about the models for the long-term prediction. We call them the global circulation models, or GCMs. They're based on 5 variables.
When you get right down to it.
And 5 variables do not cover well the decadal effects that were mentioned earlier this evening. And so they can't be in there. And it's drawn some people that are new to climate science, although they're well trained and they're brilliant people, they're still new to climate science. They weren't trained as climatologists. They come into it because of their expertise in adjacent things. And they will say, look, the carbon dioxide is now the big forcing element of the 5. I'll bet these other 4 don't make any difference anymore, like the change in the brightness of the sun. But they will still make a difference. Why, it's become almost like having CSI. Only now we're going to call this climate scene investigation.
And there's a lot to investigate. There's no doubt about that.
This is a whole new career field to determine if the climate effect in our local area is indeed due to a global scale change, or if it is just the natural variation that we get in this world that takes place over a year, or 5 years, or 10 years, or 30 years. And the 10 to 30 years of the things we talk about is the decadal scale variability.
Are there any holes in the information that you wish you had? You talked about upper atmosphere information. There's a Vortex 2 project that's doing a scientific study on more severe weather and tornadoes. Is there a gap in the information or a study that's taking place that you know of that you're really looking forward to seeing the results?
I don't know if there's a study going on, but I think one place, certainly from a long-term climate perspective, is our understanding of oceans. Anything going on over the oceans or within the oceans, we have a very difficult time with getting information because, as Steve was talking about, most people don't live in the ocean. There are a few island places, but there's not a lot of on-the-ground information from ocean sites. And that also includes the southern hemisphere, which is mostly ocean and which is not highly populated. So if you looked at where our observations are, they come from places where people live. That makes sense. But if we're trying to look at sort of global scale climate, which I'm not always sure we should be looking at global scale. We should be looking at, what's happening in Iowa, what's happening in Minnesota, what's happening in the upper Midwest. But all of these things fit together. But oceans, it turns out, have a big impact on the climate, on the weather that comes our way. What kind of front are we going to have? Is it going to be wet or is it going to be dry, and that sort of thing. So that's one place where I think it would be great to have on the ground, so to speak, information, but we're just never going to get it.
I'll go ahead.
No. Go.
I've been talking more than you.
I was going to take us another direction. Stephanie asked, where are the holes? What are we missing? And I actually have an expertise in snow in mountains and snow water equivalents and snow water supply. And there's a hole in the research, or in our understanding, in mountains are water towers for much of the globe. Now, we don't have mountains here in Minnesota or in Iowa, but we do rely on snow melt to an extent. The people who manage dams, not dam managers, but who manage dams and water supplies, it's very important for them to understand not only how much water is in the snow, but when will it melt? When will it be coming down the river, down the pipe, so to speak? And something that is changing is the amount of particulate matter in the atmosphere, dust. Understanding how much dust is landing on snow when. So when is snow going to start melting? And what we've been seeing in the last few years is managers of dams have been having an extremely difficult time because snow is melting a little earlier in the season. And so there are now some studies going on about dust on snow. It sounds trivial, but this is huge in understanding this. And so you asked that. That, for me, in the areas where I work, this is critical to understand this and to identify these networks, and helping managers of dams, which of course is water supply for drinking, water supply for agriculture, and flood protection on down the way. Very important to understand this bit of research. Yeah.
Craig?
If I really, something I would really love to see would be a computer model that forecasts the formation of individual thunderstorms.
Oh yeah, that would be awesome.
And circulations with it and where tornadoes would occur. We can't do that right now. We look at broader scales and then essentially surmise areas where this would occur. Until you see it form, you don't really know you have it. But I think it'd be just great to be able to have running a model that says at 2 o'clock this afternoon a thunderstorm will form over Austin. And then it'll move to Rochester, in this amount of time. But we're probably not close to that yet, are we?
We're not quite there. I mean, there are some... we talk about, when we're looking at climate change, we're talking global, and maybe we need to get down local. They do run some fairly localized models that do try to make a prediction of what the radar will look like at a certain time, and and they do okay, but it's not down to that scale of a town. It may say, thunderstorms erupt. You could see the thunderstorms coming over southern Minnesota, but it may be on the order of Mankato versus Austin. So it's 100 miles off. So it's not that level of predictability where you can say, cancel the picnic. That's not there yet.
All right. Well, I do want to remind viewers that if you have a question for any of our panelists here today, be sure to give us a call or also email us at ask@ksmq.org, and we will do our very best to answer that question. Weather is certainly one of our favorite subjects to talk about. And during our remaining time together, we'll have our guests share some of their most interesting weather events. And we'll start right here with a quick tape.
In addition to being a common topic of conversation, weather can also be fascinating, frightening, and quite dramatic. Our region experiences many of the most extreme weather events such as floods, tornadoes, drought, hail, and more. There's no doubt about it, weather is rarely dull.
All right, Don, we're going to let you start with your most interesting weather event, and it's actually one we've talked a little bit about already, but go ahead and share with us what...
All right, I sent a few slides in, and so to make climate change digestible for the public, I sent a few slides, and we'll quickly go through these. This is a slide showing the decrease in the areal extent and the volume of glacier ice around the globe from 1980 to the present. And I want you all to see that it is decreasing drastically. The black line is all glaciers, and the red line is some reference glaciers. Next slide, please. Can't talk about it. There we go. All right, now this is an increase in temperature across the globe, including the oceans, from 1880 to roughly the present. And I want you all to see the trend that is there. It is indeed increasing. There was a spot between 1940 and 1980 roughly where it decreased, but we've been on a pretty steady increase since 1980. There are indeed anomalies that go up and down, but I wanted you all to see that. On the next slide, let's see what that one is. This is differing the temperature changes since 1880 by the northern hemisphere in red and the southern hemisphere in the blue. And in general, the southern hemisphere is a little bit cooler because there's less land. It's all ocean observation. And it's harder to heat up and cool down water. It retains heat a little better. The next slide. And I'm going very quickly because I have only 3 minutes to do this. This separates out the land from the ocean temperatures rather than the hemispheres. Aggregate once again from 1980 to the present. And I'd like you all to see how the land is heating up quite a bit more than ocean temperatures. But once again, we've got this drastic increase happening from roughly 1980 to the present. There are some ups and downs in the system, but that's what's happening. And in the next slide, this is all the global temperatures put together, ocean together, hemispheres together. These are, excuse me, I'm incorrect. This is the Met station, so this is only land-based. Once again, similar patterns. And our next slide.
Okay, that is the last one.
So what I'd like to say is online, I believe on the website where all these graphs came from, this is posted online. You can go to the National Climate Data Center, you can go wherever these are linked to and so on, and find the same kind of data yourself.
Any helpful hints for people interpreting? And these charts are very useful and very user-friendly, but any advice you give them on interpreting the data actually from any of you folks? I'm sure you've all seen
one caveat I have is I would trust more than the one single researcher's website. I would look at the large research consortiums and the large government agencies. They're going to put something out that has been vetted by at least a handful, if not hundreds or even thousands of scientists.
Okay.
There are a few naysayers out there, listen to them. But if there are 1,000 voices, for example, on the IPCC report, saying this is what we think's happening, versus the 2 that say, no way, well, what do you want to listen to?
To be educated consumers of information. All right, Kathy, we're going to take a look at your pieces next, and we're going to start with the one about hurricanes, and I would love for you to share the story of your dad that you shared with me earlier and his experience with a hurricane, because we don't get those here in Minnesota.
We don't get hurricanes in Minnesota. We have sometimes gotten the remnants of hurricanes actually making it to Minnesota, but my father, who is a retired dairy farmer, I grew up in southeastern Wisconsin on a dairy farm, and when my dad retired from farming at the age of 60 he went to the Peace Corps in Jamaica, and was in Jamaica in 1988 when Hurricane Gilbert went across the entire island, which on the bottom of the screen there is the smallest island of which those dots are directly passing over. So my father was there, and being a native Midwesterner dairy farmer thought, how bad can it be? It's a hurricane. I've lived through severe storms and tornadoes and all this kind of stuff. And he did tell me later that he was duly impressed by this hurricane when the garage from down the street landed in his front yard, and also by the devastation that he saw when he was there on the island. And this little image just goes to show here for Iowa that some hurricane tracks actually have made it either right into Iowa or really, really close. Not very many, but we have had a few. So hurricanes, maybe not something we would normally think of as a weather story here in the upper Midwest, but things do happen. The next couple are just a couple of images of clouds, because I think all of us, if you have grown up in the Midwest, actually if you've grown up anywhere, you like to look at the clouds. And so in the summertime we get these spectacular thunderheads, these tall cumulonimbus where you can see the tops of them essentially reaching the top of the troposphere, and they starting to spread out. And also the mammatus, which are very ominous looking when you do see them. Sometimes they're kind of green and they make you sort of get a little creeped out.
Run
run for the shelters. They're not always a sign of severe weather, but they certainly can be.
All right, great photos, great photos. Steve, we're going to turn to your photo next. You shared with us a picture, I believe it was, of a moon halo.
Yeah, moon halo, typically seen in the really anywhere in the country, more in the fall or winter when you get the a high layer of crystalline cirrus clouds that are uniform, thin, and you can get this bright halo effect. And you can kind of see it in the sun, but especially the moon at night. It really can be very vibrant and very vivid. And I was a greenhorn meteorologist for the National Weather Service down in Lake Charles, Louisiana in 1988. I saw Gilbert on the radar there, and the old WSR 57 model number 2. But I took a call about 10 o'clock at night. I was working the swing shift, and in South Louisiana, it can be hard enough to understand sometimes some of the dialect you get, because you get people of the Cajuns, and there's some other classes down there that it's very difficult to understand. And this woman was just frantic, and she's just uttered out, "What that paper?" And I couldn't understand it. And finally, I just got her to go slow, and she said, "What dat be up there?" And I puzzled, and it finally dawned on me, it was the moon halo. And she thought something bad was going to happen. So the superstition. So if you've ever been down to New Orleans and gone in some of the French Quarter, there's a lot of voodoo and things like that. And so this halo really had her unnerved. So what most people thought was very beautiful, she was frantically afraid of the halo. So as a greenhorn meteorologist, I learned it's not just the tornadoes. It can be anything out there.
Yes. Well, and you also brought with you a sign that our folks in the region may be able to see in the coming months and years.
It's been a new highway road sign that was, the National Weather Service had a lot of work in getting this done, called "When Flooded, Turn Around, Don't Drown." And so local communities can purchase these. It's in the Federal Highway Manual, and they can get these signs in areas that flood a lot when it rains, because we know we can't build all the roads around that. And my flood story is, I'll be quick about it, was the July 23rd, 1987 Twin Cities flash flood. Twin Cities had about 12 inches of rainfall across the southern part of the metro. I happened to be at the Ordway Theater, which was fairly new at that time, seeing South Pacific, and in the first act, it sounded like timpani started playing. And I'm thinking, there's no timpani in South Pacific. And then intermission, went outside, and it was just flashes of light and everything, and just thunder and torrential rain. Thought nothing of it. Went back in. Continued the whole second half of the musical, and we went back out, and we had to go get the car. And we came back, and listening on the radio, roads were closed everywhere. Everywhere. All over. And we had to drive from St. Paul to New Hope, which is on the west side of town. We ended up having to. 94 was flooded in town. We had to go north to 694 and then come all the way around the town, and then to find out all the roads were flooded to get to our house. We turned around and didn't drown several times. Finally got home, and it was flooded at home, and there was water in the basement. So it just,
and what a great segue to Elwin's as well, because he is going to share with us a little information about 100-year floods and how it doesn't take 100 years to see them anymore.
I try to be a little quicker on some of these things than my friend here. One day I stopped to talk right in the middle because I heard the wind change direction as I was speaking. And I said, "I am now done speaking, and if you live east of here, head home as I'm going to. If you live west, you've got another 20 minutes. And everyone thought I was kidding, but I did go out the door. And people that didn't leave right with me did not get home that night.
Oh, all right. Well, let's run through these quickly.
We are seeing a lot of changes. We put weather stations into Iowa. In 1893, we put in 35 of them that are still there. Those first 4 years, we had 60 days with precipitation during the year. During the past 4 years, we've had more than 120 days with precipitation. We're now getting twice as many rainy days as we did 110 years ago. And across the country, you see the larger the black dot, the greater the increase in the amount of precipitation that's received in the area. The open dots have less. The blue area is the area of the U.S. that has received about 10% more annual precipitation than back in the 50s. The red areas actually got a little drier. For Florida, the hurricanes quit. And this changed our floods. On this chart, you'll see a black line near the bottom that's sloping up. That's the average annual flow of the river, the trend line. It has exactly doubled in northeast Iowa and southwest Iowa and southern Minnesota. And here at Austin, look at the right. These are the flood years. And in the right-hand side of the picture, there are three times, actually 6 times as many floods in that 30-year period as the previous 30 years. 10% more rain, double the water in the rivers, and 6 times as many floods. We'll let this be my last slide.
All right, very good.
But this means that 100-year floods now are expected every 17 years. That would be something like 1993 and again in 2008.
Wow, that is a lot. Peter, you brought some pictures for us that have to do with snowstorms and some lightning. So let's take a look at some of those.
Oh, there's a good lightning picture. Unlike southeast Minnesota and Iowa, in the Twin Cities, we're in a bit of a drought. We're in a severe drought. And this is from 1998, which is probably one of our last real big severe seasons we had in the metro with lots of storms during the season. This is one of them. This is on my deck, and I had an old pawn shop camera, and I just left the shutter open and just waited for lightning to hit, then closed the shutter and crossed my fingers, and I got a good picture out of it. So it was one of those kind of lightnings that just kind of fork out across the bottom of the thunderstorm, and quite a nice display. So it's before digital camera, it was pretty good. This is just I love some winter pictures too, because any meteorologist worth their salt has a whole shelf full of cloud pictures. Trying to take a good wintertime snow picture is a challenge, and I did my best shot. And this was just a run-of-the-mill, like 10-inch snowstorm or so. This is in the middle of it, and what I've been trying to do over the years is try to take a picture when it's snowing the heaviest, because it's so hard to show up on film. It's hard to get anything below a quarter of a mile visibility, just falling snow, not blowing snow. So I gave it my best shot there, and you can't see the flakes, but you can kind of tell. And I had to throw in one picture of the Halloween blizzard. It's interesting, if you go to the Historical Society in Minnesota and look up Halloween blizzard 1988 or 1991, you'll have 0 hits because it's not historic yet. You have to wait a certain period of years for it to be historic. So when we try to do recaps of the Halloween blizzard, it's very hard to find pictures because we don't have any. And this is the best thing I could come up with, is my brother-in-law shoveling. And what's interesting about the pictures, you notice the pavement is perfectly clear because it was still warm. And that was one of the biggest impacts after the storm. The days after that was, Steve will attest, is the washboard road. So it happened after that. And with Iowa, that was the costliest ice storm in history, I think, was the Halloween blizzard. So, and this was just a couple of years ago. I had to throw in a few cumulonimbus clouds in there. This is towards the end of the night and moving off to the east, and just a real nice picturesque shot of some clouds. And thankfully the storm's moving away from me at this point. But never saw a tornado, but I've seen some interesting cloud pictures.
Great. All right, and Craig, you are a meteorologist worth your salt. You have some beautiful cloud pictures.
I have a bunch of photos. I could tell a quick story first, if I could, though, and then we'll get to the photos. I'm from Cedar Falls, Iowa, and last year there was a major flood on the Cedar River there, and also the Parkersburg tornado was just west of Cedar Falls. And our church had work crews out for damage for these. I went to a home that I went to work on flood damage. There were people on the roof fixing their roof from the tornado that hit them about 3 weeks earlier than that. So this is one house that was hit by a tornado followed by flooding from the Cedar River, all in less than a month. So I don't know what the odds are of that, but they were feeling pretty picked on. This is a shot of a thunderstorm. It's pretty classic. This was taken in northeast Iowa, and you can see the classic anvil top on that storm as the updrafts flatten out across the top. It's underneath that anvil where you'd see the mammatus-type clouds. And we can go on to the next photo here. There are some mammatus clouds. Now, Kathy's were a different color, but these were more of a yellow color, and that's just because of the the sunlight, as it gets near sunset, was changing colors and putting kind of a yellow cast. Interestingly enough, pilots who have flown close to those, I don't know why they're there, but they were, report those to be rather transparent looking and not dense as they look from the ground. These are some cirrus clouds at sunset, and you can see that the strong winds of loft blown those into kind of like long fibers or fingers, and it's actually a cirrus fibratus cloud because of the fibers in it. So those clouds are always made out of ice crystals. This is a sundog. Also is taken around the Cedar Falls area, and you can see the sundogs on either side there of the sun, and that in this case is caused by snow blowing and the sunlight being bent as it goes through the ice crystals, causing those glints of light. This is something that's really cool to me. It's called a pileus cloud. That's the cap. It's on top of this building cumulus cloud, cumulus congestus actually. And what the cloud is doing is lifting a layer of moisture, of moist air. The air is flowing over the top of that cloud like air going over a mountain, and so it's creating this thin cap cloud. And once it got higher, that cloud actually dissipated because drier air evaporated it. This is a boring cumulus cloud. This is something everybody would see, nothing spectacular about it, but very common here on summer afternoons. And these are altocumulus. It's a mid-level cumulus cloud. Actually, alto means high, but it's higher than the lower type cumulus cloud, so it's in the mid-levels, if that makes any sense whatsoever. And the air is really kind of rippling there. And this is an altostratus type cloud, but it has some ripples in it, and just caused by kind of an up and down motion, sort of like waves you would see in the air. And this one here is a big old cumulonimbus. It's like a bomb went off. And actually, my wife and daughter were underneath that in a dress shop buying a wedding dress. This was a number of years ago. So I have ground truth on what actually happened under there. And they did survive it. So it rained and there was some small hail and wind. But something we see right here in the summer. That's another one there, another cumulonimbus cloud, big old anvil on top of that. That storm was about 40 miles away. And so you can see the fibrous look of the cirrus on top, and then the cumulus structure underneath with those big billowing clouds with the pink on them there. So,
right. And these cloud pictures are fantastic. Tell the story about how that got you to be a meteorologist.
When I was a child, like 5 or 6, 7 years old, I was interested in the sky. And so that's what got me fascinated about science and about weather, and how does that work. And so that's what got me going. I even had my first camera and took a lot of photographs, and I just have moved on to digital now from film, but I still get the same kind of rush when you look at the different kinds of clouds.
Well, I'm so glad all of you were inspired by your various weather experiences to get into the fields that you have been in, and we appreciate you coming to share this information and explain some of this weather, and hopefully folks will be able to share their thoughts with you at a post-program on our blog as well. So some terrific photos there. That is awesome. Well, we can't help but be immersed in the weather, and here at KSMQ, we always encourage our audience to be active viewers. And I encourage you to visit our website, ksmq.org, to find links to the various organizations and programs we've discussed here tonight. In addition, our panelists will be sharing some additional thoughts on our KSMQ blog. So if you'd like to be part of that discussion, log on to blog.ksmq.org and share your thoughts as well. Also, if you have a weather event photo you'd like to share, please feel free to include it. We appreciate everyone's participation here to help us increase our understanding of the weather events and technology. Thank you to our panelists and to our viewers. I hope you'll tune in next week when Cities on the Move takes a tour of Austin, Minnesota to explain the process of economic development. We'll also meet a native son who has just completed his freshman year at Harvard, as well as talk with Bill Klingerman about the purpose of the Sentence to Serve program. That's Tuesday, July 7th at 6:30 p.m. on KSMQ. Thanks for joining us. Good night.